Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on equilibria. This is topic 7 for the CIE specification. So this is the Cambridge Internationals A-level specification. So if you're studying CIE chemistry or A-level chemistry, then this video is perfect for you because we're going to go through all the different things that you need to know regarding equilibria for this topic. Obviously these slides that I'm using here, they're just PowerPoint slides, and you can obtain these and purchase them from the test shop, which you can use to supplement your revision if you wish. If you click on the link below in the description box, you can access them there. Obviously these are all available on the Allery Chemistry YouTube channel as well, as you can see, and there's other CIE topics on there for the full range of A-level. Please hit the subscribe button. That's a massive help. It's a huge support. And share it with your friends as well, so they know where to find some CIE resources as well. So like I said, this topic is specifically looking at equilibria, but I have the full range of topics on the Allery Chemistry YouTube channel as well. Okay, so let's make a start. So equilibria, this is obviously for the year 1 specification. So equilibria, the way CIE do it now is they've kind of split the some of these topics into year 1 and year 2. So you'll see the year 2 stuff obviously in a later topic. So this looks at the year 1 content, or the AS content. So we're going to start, before I do this actually, there's a lot of, with the CIE topics, they kind of overlap quite a lot compared to some of the other topics as well. So I might refer to some previous topics as well. It's a good idea to kind of familiarise yourself with the previous ones, so topics 1 to 6, before you come on to this. But a lot of the stuff in here is going to be quite new anyway, so it's not mandatory that you need to know the previous topics. So, okay, so let's look at what a reversible reaction is. So reversible reactions are basically where reactions can go forwards and backwards pretty much, so hence the word reversible. So reversible reactions are represented by this type of arrow. So it's a forwards and backwards arrow, like half arrow, I suppose. To be honest, a lot of reactions are reversible. Sometimes you don't necessarily show them as reversible unless we're actually talking about equilibria. But yeah, so I mean, you'll see this quite a bit, obviously, in this topic in particular. But an example is A plus B will form C plus D, and vice versa. Basically, that's how it's structured. So, looking at I suppose a graph. This is to do with equilibria. So it's to do with obviously forwards and reverse reactions, and look a little bit at rate of reaction to an extent as well. But the forward reaction, so let's look at, like in this example here, forward reaction, initially reactants are used up quite quickly because there's loads of them, but it slows as their concentration drops over time. And so this graph kind of shows that for a reactant. Now naturally for a product, products are obviously formed quite quickly as well, and eventually you end up with a reasonable amount of product being formed. So obviously this is kind of like the backwards reaction. So if we look at equilibria, so equilibria is the point at which the rate of the forwards reaction equals the rate of the backwards reaction. So rate is quite critical here, and we call this a dynamic equilibrium, okay? And the concentration of each substance remains constant at that point, okay? Now it's really important you do not get this confused with it's not the same amount as the amount, it's not the same thing, as the amount of reactant. So the amount of reactant may well be different, the amount of reactant and product may be different. It's the rate at which it's produced is the same, so it's the speed at which it's produced. That's really important. So when we're looking at equilibrium, and from this forward onwards, or kind of this moment onwards, throughout or the whole topic, that's what you need to kind of have in your mind, okay? So don't get them confused. Okay, and obviously all this only happens in a closed system. So basically, your product cannot escape. So you kind of put a lid on top of the reaction vessel or kind of contain it, and that's how a dynamic equilibrium is established in a closed system. Okay, so this brings us nicely onto this chap here called Lecitelia. And Lecitelia was a Frenchman who developed a principle where he stated what would happen if we change conditions to an equilibrium reaction. And this is always an interesting concept because it's kind of like, it's quite behavioural, I kind of see it as, to try and explain what's happening. It's almost like a, I don't know, some kind of stroppy child or something like that. So you'll see what I mean when we go through it. So this is the fella here, and he's called Lecitelia. He's a French, like I say, he's a French scientist, and he said if a reaction at equilibrium is subject to a change in pressure, temperature, or concentration, then the position of equilibrium will move to counteract the change. This is kind of like where the child analogy comes in. So I've got a 6-year-old and he's good as gold, and he's there's no issues with them whatsoever. But sometimes with children, and he's got a bit of a sometimes he's got a bit of a how can I say it? He's got a bit of a trait where if I say one thing, he'll probably do the opposite. Probably just to wind me up, I think. But in a good way. He's not bad or anything like that. But he kind of does that. And imagine, I suppose children will do that. Even adults do it, to be honest. Some adults will do it, and they'll kind of do the opposite just to wind people up. So reactions are kind of like the same as well. So, if there's change in condition in a reaction results in an equilibrium shifting to the left, we make more reactants in this example here. So you've got 3 molecules of hydrogen reacting with nitrogen to form 2 molecules of ammonia. Okay, so if the change in conditions, whatever the conditions are, whether it's pressure, concentration, etc., results at shifting left, then we make more reactants. Yeah, that seems fair enough. And if the change in the condition results in equilibrium shifting to the right, then we will make more products, won't we? So you can see we've got 2 halves to this equation, and we can change some of the conditions to either produce more or less product or reactants. Okay, so this is where it gets a little bit complicated, because this is where Lecitelia's principle comes in. Okay, and in this one we're going to change concentration and see what impact changing concentration may have on a reaction. So if we increase the concentration of a reactant or product, then the equilibrium will shift to try and reduce the concentration. So the opposite will happen if the concentration is decreased. So basically, you try and do something to it, and it will try and do the opposite. See what I mean? So this only works in homogeneous equilibria, so this one here. So this is where the reactants and the products are in the same state. So in other words, they're all gases, all aqueous, all liquids, all solids, whatever it is. Most of these are aqueous anyway, but so in this example, we're going to bring that example back, and this is the Haber process, which I'll talk about a little bit more actually in more detail, because you do need to know about the specific dynamics of that reaction. But if we increase the concentration of H2, equilibrium will shift to the right to use it up and reduce the concentration, and so therefore we actually get more NH3 produced. So let's have a look at this in a little bit more detail. So if we increase the concentration of H2, so we're going to add more of this into the reaction will say, I want to try and get rid of this or use it up. So it'll react with the nitrogen that's available in there, and as a result, you'll get more ammonia. Now, if you're in the business of producing more ammonia, that's a pretty good thing. However, if we increase the concentration of NH3 in equilibrium, so let's say we're going to put more of this into the reaction vessel, then it will shift to the left and it'll try and use it up. It's saying, well, we're putting more of this in, so it'll say, right, well, actually, I'm going to produce more of this instead. So equilibrium will shift to the left and we'll get more H2 and N2. So we get various different scenarios there. Okay, let's look at a different condition changing. Let's see if we can change pressure instead. So if we increase the pressure, the equilibrium will shift to try and reduce the pressure. I think you're getting the theme here, aren't you? So the opposite will happen if pressure is decreased. So again, this only works in homogeneous equilibria. So if we increase the pressure, equilibrium will shift to the side with the fewest number of gas particles, and this will reduce the pressure, and so therefore more ammonia will be produced. So let's have a look at this. So if we increase the pressure in equilibria, okay, so we increase the pressure, it will shift to the side with the fewest number of gas particles. So we've got 4 gas particles on the left here. So we've got 3 and then 1, and you've got 2 on the right here. So if we increase the pressure, it's going to move to the side with the fewest number of gas particles to try and reduce that. So you'll actually get more ammonia produced. And obviously if we go the other way, if we decrease the pressure, it will shift to the side with the most number of gas particles, which is going to be on the left hand side, which is on here. So you'll get less ammonia produced and more hydrogen and nitrogen produced. So I think you're kind of getting the idea, or at least I hope you so anyway. Okay, let's change one other condition. Let's change temperature and see what effect that will have as well. So if we increase the temperature, the equilibrium will shift to try and reduce the temperature, and the opposite will happen if the temperature is decreased. So I think, like I say, you're getting the theme here. This one's a little bit trickier, but it kind of feeds onto topic 5, where you looked at thermals and enthalpy changes. So this brings a little bit of topic 5 into this one here, into topic 7. So if we increase the temperature, equilibrium will shift in the endothermic direction, and this will reduce the temperature, so you get more N2 and H2 will be produced. Now with these reactions, you will be given an enthalpy change for the reaction, and the figures that you're given, as you can see highlighted in yellow here, will be showing the enthalpy change moving in the forwards direction. So this is moving forwards. So this reaction is an exothermic reaction moving forwards because it's got a negative sign in front of it. So if we increase the temperature, it's going to move to the endothermic direction, which is the other way, backwards, and it means we'll get more H2 and N2 produced. If we decrease the temperature, again, same reaction, then equilibrium will shift in the exothermic direction, and this will increase the temperature, so we'll get more ammonia produced. So the key thing here is looking at the actual figure of the enthalpy change, because that's going to tell you what the enthalpy change is moving forward, and obviously the reverse reaction is just the opposite of that. So in this case, the reverse reaction is endothermic. Okay, so let's look at catalysts and what effect catalysts have on Lecitelia's principle. This is really straightforward. Catalysts have no effect on the position of equilibrium. So remember, this kind of comes back to what we said at the start, that equilibrium is to do with how is to do with the rate of reaction. So when the rate of the forwards reaction equals the rate of the backwards reaction. So all a catalyst will do is speed up both forward and reaction equally. So it means that equilibrium is probably established quicker, but it doesn't actually have any effect on the actual position of equilibrium at all. Okay, so there we are. So it'll have no effect on the yield. You're not actually producing anything more using a catalyst. Okay. So this is where we're now going to look at something called Kc. Okay, so this sounds like a bag of peanuts. It's not actually, although there is one called KP later on, as you'll find out. Other brands are available, of course. So this is Kc. So Kc is something called the equilibrium constant, and again, this is suitable for homogeneous systems. So basically, where everything's all in the same state. So the Kc expression can be worked out from the molar concentration in a reaction. So this feeds on topic 2, which when you looked at the molar reactions, etc. When I know we I talked about topic 2 a lot, and I said you are going to know all these different parts. A lot of topic 2 kind of dips into many other topics as well, because it's about molar calculations and things like that. So it is quite obviously fundamental that you know that. So this is relatively straightforward actually to work out. So the molar values in front of each species are powers in the Kc expression. So we've got an example equation here, which is 2 lots of A plus B will form 2 lots of C and D, and it's a reversible reaction because you've got your arrows in there. So basically, you can see here that when you write a Kc expression, here's an example of one here, then the numbers that sit in front of the letters correspond to the power that you put in the Kc expression. And the Kc expression is always going to be products over reactants. Okay, so your products are C over C and D, which is here, and reactants is A and B, which goes in the bottom there. And obviously you put your powers on there. Your square brackets represent a concentration of something. Okay, so that's really important. You'll see that a lot in chemistry actually, where you see square brackets, that means concentration of. Okay, so we can write the Kc expression for a proper reaction this time. So we've got 2SO2 plus O2 will form 2SO3. Okay, all these are in the gaseous state, so it's homogeneous. So all reactants and products are in the same state, as I mentioned before. So all reactants and products are included in the final Kc expression. Okay, so the expression in this case is going to be SO3 squared divided by or over O2 and SO2 squared. Simple as that. Dead straightforward, as you can see there. If it's not, we'll look at a heterogeneous one as well. It kind of slightly changes a little bit, but it's pretty straightforward, as you can see. It's not too bad. Okay, so let's have a look at a heterogeneous one then. Let's look at where they're not in the same state. So you can see here that we've got the molar values in front of each species. So you've got a gas, a solid, a gas, and a gas. So this is heterogeneous because we've got a solid mixed in there. So you can see we've written our Kc expression. There's your products, there's your reactants. And solids and pure liquids are not included in a Kc expression. So we're looking for concentrations only, molar concentrations. So you can see B has been omitted from this completely, okay, because that is the solid there. So that's the only difference. There's no real change in terms of how you write it. But let's look at a specific equation here. So we're going to write the Kc expression for the following reaction. So you've got carbon plus oxygen will form carbon dioxide. So heterogeneous reaction, we are not including the solids or pure liquids in the final Kc expression. So this is because their concentrations actually remain constant. They don't actually change in the reaction, so we just ignore them. So here we're just looking at O2 and CO2. So CO2 goes in the top and O2 goes in the bottom, and that's the final Kc expression there. Nice and straightforward, as you can see. So let's kind of work on this a little bit more, and let's kind of do something with this expression. So we know how to form it from a reaction, and we know how to write it out properly. We now need to kind of put some numbers in there, because it wouldn't be chemistry without a bit of maths, would it? So here we are. We've got this equation again. So the molar values again in front of each one, obviously they represent the powers, as we can see there. So you got your products, you got your reactants, and obviously your square brackets, so we know what that means. So here we're going to use some figures here. So we're going to write the Kc expression, and we're going to calculate the value of Kc of the following reaction. So we've got the concentration of SO2 is 0.4 moles per dm cubed, concentration of O2 is 0.2 moles per dm cubed, and the concentration of SO3 is 0.8 moles per dm cubed. So there's our full reaction there. So the first thing we need to do is write out your Kc expression using that equation there. So there's our Kc expression. Okay, it's all homogeneous, so everything's thrown into the expression there. And really simply, all we do is just put the numbers in where the square brackets are. So 0.8 squared divided by 0.2 divided by 0.4 squared, dead easy. And that gets us a Kc value of 20. Okay, now we need to work out units. Now the units can vary depending on obviously what we're reacting. So how we do the units is we basically write the units of concentration, which, if you can remember from topic 2, is moles per dm cubed. So we've got a concentration here squared, so effectively we write the units of concentration twice on the top line. On the bottom line, we've got a squared and a single one here, so we write that 3 times on the bottom. And what we're going to do is then cancel out the units top and bottom and see what's left. So let's have a look. There we are, cancel that out. And that bit on the bottom, if you've got units left on the bottom, you flip it onto the top line and you invert the different units here. So this would be mole to the -1, see, dm to the 3, because that's been moved up to the top line. We invert it, and that is the units in this case here. You've got to remember, you must work out units depending on the reaction that you've got here. The units will differ depending on what you have. There's no fixed units here, so just make sure you're aware of that. Okay. Right, let's look at something that's a little bit more complicated. Okay, so we now, obviously we put the units in that, we've worked out Kc, which is brilliant, but we can actually work out the concentration of a species in equilibrium before we actually work out what Kc is later on. So in that example, we were given all the concentrations, we just put them into the equation and worked out what Kc is. So they might be a little bit meaner and not actually give you all of the concentrations. So let's look at an example here. So nitrogen dioxide decomposes according to this reaction. So we've got 2 lots of NO2 plus 2NO, will produce 2NO plus O2, as you can see on there. So 33.2 grams of NO2 was heated in a vessel with a volume of 9.65 decimeters cubed at 450 degrees Celsius, and 6.88 grams of O2 were found in the equilibrium mixture, and so we need to calculate the value of Kc. Okay, so the first thing we need to do is we're going to use an acronym. Okay, we like throwing in a few acronyms here. So I'm going to use the acronym ICE. Okay, nice and cold. Actually, as you can probably tell, I'm filming this in August, so it's far from cold. It's actually really warm. But anyway, so use the acronym ICE. ICE stands for initial moles, change in moles, equilibrium moles. Okay, and you can see I've kind of put the table down. I'll call it an ICE table. I'll put the ICE table down there, and effectively all I've done is I've put the acronym initial change in equilibrium, ICE, which is down there, and I've put the kind of components of the equation in their own separate headings here. So 2NO2, 2NO, and O2. So that's kind of how I've structured it there. And what I'm going to do is I'm going to use this to help work out what this equation is. Now, you might have a different method of doing this. There's never any right or wrong way of doing this at all. This is just a way of, so you can see where I'm getting the numbers from. But you can more than happy use this if you want to work these out. So, first thing we need to do is work out the number of moles of NO2. And remember from topic 2, number of moles is mass over MR, okay? Because we're looking at, obviously, the mass of the substance that's being used divided by the MR. So the moles is 33, so the moles of N2, is the mass over MR. So the number of moles is 33.2 grams, because that's what we're told here, divided by 14 plus 16 plus 16, because that's the atomic masses, or the relative molecular mass, of NO2. And then what we do is we write that in there. So that's the initial number of moles of NO2. Now, the moles of product right at the start of the reaction of NO and O2 is going to be 0, because we haven't actually formed anything yet. All we have is a beaker of NO2. Okay, so that's why this is 0 and this is 0. Okay, so we then need to work out how many moles of O2 we have at equilibrium. Okay, so again, we do that by taking the mass and dividing it by the MR. So we know, because it tells us in here, that we produce, so we've got a volume of this, and we've got 6.88 grams of O2 were found in the equilibrium mixture. Okay, so that's how much we're in the equilibrium mixture. So we can put down 6.88 grams, that's the mass, divided by the MR of oxygen, which is O2, and that gives us 0.215. Okay, so that's the equilibrium amount. That's how many moles were in equilibrium. So we know the mass, we've worked out the moles, and obviously the change is plus 0.215. That's how much it's increased by. Okay, following so far? Good. Right, so we're then going to use the molar ratio here, okay, in that equation to work out the changes for the other species. Remember, products have got to increase because you're making them. So you're obviously going to end up with more product at the end, or at equilibrium, than what you are at the start, aren't you? And obviously your reactants are going to decrease because they're being used up to make the products in the first place. So, here we go. So let's look at NO first. So we know with NO, we have twice as much NO as we do oxygen. So the change is going to increase because you're going to get more NO produced. And all we're doing is we're taking the number of moles of oxygen, multiplying it by 2, because we've got 2 lots. So that'll give us a change, an increase of 0.430. So therefore, at equilibrium, we have 0.430 moles at equilibrium. And obviously, the NO is in the same ratio as NO2 is in the same ratio as NO. So the change is going to be the same number, but it's going to be decreasing. So it's going to be going down by the same amount. And so what we do is we take the amount that we had at the start minus 0.430, and that means at equilibrium we have 0.29 moles at equilibrium. That's the hard bit. Okay, once you've populated this table, you've got all the figures you need now to just do what we were doing before. Okay, so we're then going to work out the concentrations, because remember your Kc expression must be in concentration, okay? So the concentration of NO is the number of moles divided by the volume. So the volume was 9.65 decimeters cubed, so it's already in decimeters cubed, so that's fine, that's good. So we just do 0.430, which is that number there, 0.215, which is that number there for oxygen, and for NO2 it's 0.29, and divided by the same volume, and we get all of our concentrations there at the side. Then we can put all that into your Kc expression. So we write our Kc expression first. So remember, it's products over reactants. That's it there. You then put all your numbers in that we've just calculated up here. So chuck them in there. And then you should get a value of Kc of 0.050. Now again, we're going to work out our units. There's our units at the bottom. So we're going to cancel them out. Now this time the units are already on that top line, so we don't need to invert any units. We literally just write moles per decimeters cubed. And that's basically how you work that out. So the key thing is this ICE table, initial change equilibrium, and you're using, this is stoichiometry, this, where you're looking at molar ratios in an equation. You're using that equation to work out the moles of everything else. So remember, if you've seen topic 2, the video I did in topic 2, I talked about moles being kind of like the capital of somewhere. You can get to a lot of things by knowing the moles. And I hope this just kind of proves that, because you can see every calculation somewhere along the line involves working out moles or using moles to work out other things. So this is why the mole is so important in chemistry. Right, so we can work out, obviously, unknown concentration at equilibrium using a Kc value as well. So let's look at an example here. So a reaction took place and equilibrium was established when ethanol reacts with ethanoic acid. So at equilibrium, the concentration of ethanoic acid was 1.8 moles per decimeters cubed, and ethanol was 3.2 moles per decimeters cubed. The value of Kc is 3.5. at 25 degrees Celsius. Calculate the concentrations of the products at equilibrium. Okay, so let's write down the expression first. Okay, so remember we've got products, which are here, over reactants, which are at the bottom there. So we're just writing all them down. Now they're all homogeneous, so that's fine. Now the calculation, all we've got to do is we've got to substitute the figures that we do know. So we've got 3.5, because that's what we've been told Kc is, and we've got our concentrations down at the bottom here. So we've got 1.8 moles per dm cubed of ethanoic acid, and we've got 3.2 of your ethanol, which is here. Okay, so we put them numbers in there. We don't know what the values of these are though, your products here at the top. Okay, so that's what we've got to work out. So we need to rearrange this. Okay, so a little bit of maths here. So what we're going to do is rearrange that to get this to be the subject, this top line to be the subject. So that's going to be 3.5 times 1.8 times 3.2. So multiply them. These two figures here, these two, are going to be 20.16. Okay, so that's obviously the value of both of these. And then what we have to do is basically say that the concentration of both of these are going to be the same, because they're in the same ratio. So we can say that the square root of 20.16 will tell us what the concentration of this is here, because obviously these are the same. It's basically that times that. So if we do the square root of 20.16, that gives us 4.49 moles per dm cubed, because we can assume the concentration of these are the same. Okay, because they've got the same molar ratio. So therefore, the concentration of them individually is going to be 4.49 moles per dm cubed each for them individually. And that's basically how we use that. Okay, so what we're doing here with these examples is just using the Kc expression to work out various different things here. So, and the exam board will want you to be quite, to be quite knowledgeable on this and know how you can kind of use this equation to work out various different things. So just make sure that you're familiar with it. Okay, so what affects the value of Kc then? So what actually, what is it that kind of can change that? So we need to know the effect of temperature, concentration, and catalysts on Kc. So for temperature, Kc is only valid for one temperature. Okay, so that's really important. So the Kc value that you see there will be true for the temperature that was given in the question. So change in the temperature will change equilibrium concentrations, and hence Kc will change too. So if you increase or decrease the temperature, then the value of Kc can change as well. So if the temperature change causes equilibrium to shift to the right, so remember when we're looking at Lecitelia's principle, then the value of Kc will increase. If the temperature change causes equilibrium to shift to the left, then the value of Kc will decrease, so it will decline. So let's have a look at an example. So if in this reaction, so we've got the forward reaction is exothermic, so that's going forwards. You can see it's exothermic, so we've got that negative value there. And the backwards reaction is endothermic, so that's going backwards there. So if we increase the temperature, equilibrium shifts in the endothermic direction. So it's going to shift backwards, going to shift there to oppose the increase in temperature. And so Kc will decrease. Okay, so that will drop. If we decrease the temperature, it's going to shift in the exothermic direction, head this way, and so therefore Kc will increase at that point. Okay, and so you can see here, if we kind of put this in a Kc expression, you can probably see it a little bit clearer. So if we increase the temperature, equilibrium shifts in the endothermic direction, so it moves backwards, producing more SO2 and O2, which is this one at the bottom. So basically, the value of this will increase, and basically, if you obviously just like fractions, if you increase the denominator, so the bottom number of a fraction, then the overall value is going to get smaller, isn't it? Yeah. And then if you do it the other way, if you increase this number in comparison to this number, in other words, you produce more SO3, then the value of Kc will increase, so that'll get higher. So it's just like a fraction, really, so just kind of see it that way, and that's how we can work this out and use it that way. Okay, so concentration, the value of Kc is unaffected by any changes in concentration at all, so it will establish equilibrium. Obviously, concentration is changing anyway when we're altering this. And catalysts have no effect on the value of Kc either. Remember, a catalyst speeds up the forward and the reverse reaction at the same time, and so it just speeds up the rate at which equilibrium is established. So obviously putting a catalyst in has no effect on the value of Kc. Okay, so moving on to a special type of equilibrium constant, and this is kind of linked with gases, obviously because it's to do with pressure. So gases, and looking at the kind of chemistry of gases, has their own equilibrium constant. And we're going to look at, obviously gases have a pressure, so we're going to look at some of the different areas of this. So we're going to start with total pressure first. So the total pressure in a reaction is the sum of all the pressures of the individual gases. So that's the partial pressure. Kind of makes sense, doesn't it? So if you have the total pressure of everything is going to be whatever the pressure is of the gases that make that pressure exist in the first place. And obviously if they're kind of individual gases, they're partial pressures, aren't they? So you may be asked to use this information to answer questions like this. Okay, so we've got SO2Cl2 decomposes into SO2 and Cl2 under heating. So we've got the reaction there, as you can see. So at equilibrium, the reaction vessel contains 263 kilopascals, that's the pressure, of Cl2. The total pressure in the vessel is 714 kilopascals. So calculate the partial pressure, okay, of SO2Cl2, so that was our reactant at the start, and that partial pressure is written like that. It's a P with the reagent that we're using at equilibrium, okay. So we know the total pressure is the sum of all the partial pressures. Okay, so we can say the total pressure of the whole thing is the sum of the partial pressure for SO2Cl2, SO2, and Cl2. So it's of everything. Okay, so we can put in the numbers that we know already. So we know the total pressure is 714 kilopascals. We don't know the partial pressure of SO2Cl2. We don't know it for SO2, but we do know it for Cl2, which is 263 kilopascals because we've been told that there. Okay. So we know that Cl2, which is this here, has a partial pressure of 263 kilopascals, and there's a 1-to-1 molar ratio with SO2, so it's got a 1-to-1, and these are the products, remember, these are producing. So the partial pressure for SO2 is going to be the same as what it is for Cl2, because they're both products of each other. So let's complete this equation a little bit further, and let's put in 263 for SO2. Okay, so we've got all that there. Now what we have to do, I think you can probably see this, is we have to rearrange it to make this the subject, and that will hopefully get us our answer. So we obviously add these two numbers together, we get this, shift it round, so we're basically getting 714 minus 526, and we get our total partial pressure of 188 kilopascals. So that's relatively straightforward, hopefully. Okay, so the partial pressure of a gas, so that's what we just worked out there, worked out one of them, but that partial pressure is calculated using mole fractions. And a mole fraction is the proportion, or the fraction, of a gas in a gas mixture. Okay, so we're just kind of going a little bit further back here, taking a step back for this one. So let's have a look at an example, because I always find things like this, it's better to kind of describe them as an example. So let's take a generic equation as an example. So we're going to do 2 lots of D, which is a gas, is going to produce E, which is a gas, and F, which is a gas. And here we have 4 moles of gas. 2 of them are D, and so the mole fraction for D is a half. Okay, because you've got, it's the fraction, it's the proportion of gas in that mixture. Okay. So we need to know the following 2 equations when we're dealing with mole fractions, okay? So a mole fraction of a gas is the number of moles of gas divided by the total number of moles of a gas in the mixture. And then the partial pressure, which we looked at in the previous slide, is the mole fraction of a gas that we worked out here, times by the total pressure in the mixture. That's the one that we just seen in the previous slide. So we're just introducing another equation here just to kind of work out what mole fractions are. Okay, so let's have a look at an example here. So let's say we've got 3 moles of SO2Cl2, okay, is heated, and the equilibrium mixture contains 1.75 moles of Cl2. The total pressure is 714 kilopascals. What is the partial pressure of SO2Cl2? And we've got our reaction here as well. So this is kind of drawn upon the previous example that we'd seen there. So the first thing we need to do is introduce this ice table that we'd seen before, okay? And we're going to write out the initial moles of each gas. So very similar to what we've done before. So we know that we have 3 moles of SO2Cl2. This is right at the start. So we've got our 3 there. We haven't produced any product. We haven't produced any SO2 or Cl2 right at the start of the reaction. So that's 0 and 0 respectively, okay? So we know that we have 1.75 moles of Cl2 at equilibrium because that's what they've told us there. Okay, so the change is 1.75 and it's an increase because we're producing this. So any products obviously have to increase over that period of time. So we're then going to use the mole ratio, okay, and we're going to work out what the reactions are. Now everything is 1-to-1, so basically this is also going to increase by 1.75 and this is going to decrease by 1.75, so it's a 1-to-1-to-1 ratio. Okay, this is decreasing because it's been used up, it's a reactant. Okay, so we can now calculate the equilibrium moles for SO2, Cl2 and SO2. So just like what we've done before, there's no difference here. So we've got what equilibrium moles here, so that's important. So the mole fraction of SO2, Cl2, okay, is 1.25, so that's the equilibrium moles, that's the moles at equilibrium, okay, divided by 4.75. Now 4.75 is just the sum of all the equilibrium moles that's actually in this reaction here, okay, so that's the total amount, remember? So the mole fraction here is 0.263, okay, so that's the total mole fraction there. So we can work out the partial pressure because we now have the mole fraction. The partial pressure of SO2Cl2 is the mole fraction 0.263 multiplied by the the total pressure, which is 714 kilopascals. So this is just using the equations that we'd seen before. And then that would give you a partial pressure of 188 kilopascals. So it's just this a little bit more extended. There's a little bit more work to do, but what we're trying to do is use the similar formats as what you've used to the other equations, just to try and keep it simple, because there's nothing worse than trying to remember multiple different equations for different things. Otherwise you get a bit lost. So we're trying to use the same method to work out this as well. Okay. So this is where the Kp bit comes in, so like the peanuts. So Kp is an equilibrium constant. So this is what I was saying about special constants. So because it's a gas, we can use the partial pressures that we just worked out before, and these can be used to calculate the gas equilibrium constant, Kp. So Kp is just like Kc, it's just for gases instead. That's all. So there's nothing too drastic. So Kp is obviously for gases, as I mentioned before. So here's an example for writing a Kp expression. So here we've got compound E reacting with F and G and H, and the little letters in front tell you the mole fractions. Okay, that's coming to make this up. So Kp is written like this. It's a curly bracket instead of a square bracket like you'd seen with Kc, but the principle's the same. So this is the partial pressure of G, which is the product, okay, with the power of the number that sits at the top, which is the little g there. So there's no difference there. So it's always product over reactant. So let's see an example of where we can use Kp. So we're going to find the value of Kp for the following reaction, and we're going to have to give the units as well. So we've got two lots of A reacting with B to form C and D. Okay, given that the partial pressures are 324 kilopascals for A, 162 kilopascals for B, 182 kilopascals for C, and 182 kilopascals for D at equilibrium. Okay, so basically all we're going to do is going to write our Kp expression. So we've got Pc, Pd, and then Pa squared, and then Pb. So the reason why that squared's there is because we've got 2A there, and the little p stands for partial pressure. Okay, so that's what that stands for with the curly brackets. Very similar to Kc. I don't want you to think this is completely different. I hope you can see that anyway. So all we do, again, just like we've done with Kc, we just put the numbers in that we've just seen here, and then obviously we can work out what Kp is, which is this value here. Now, just like Kc, you have to work out the units for Kp as well. Okay, so the units here are kilopascals. So it's not moles per decimeters cubed like what you've seen with Kc, it's kilopascals. So what we've got is we're going to put the units in the bottom, the units at the top, and we're going to score them out. Okay, the units that are left, we've got excess on the bottom here. This is inverted, brought up to the top line, so it should be K to the minus 1, Pa to the minus 1. There it is. Sorry, Kpa, so Kpa to the minus 1, so it's kilopascals, that's not a separate unit. So it's kilopascals, so it's Kpa to the minus 1, which is then put there. Okay, so hopefully you can see that Kp is just Kc, but just using partial pressures instead. Okay, right, so let's look at some specific examples, and we need to know a few of them. So one of them is the Haber process, and the other one is the contact process, which are two kind of reactions, industrial reactions that actually have quite a important process, but involve equilibrium quite extensively. So the Haber process is the method of producing ammonia, and ammonia is incredibly useful for fertilizers, so fertilizing crops, and that helps obviously produce crops and food at a fast rate to feed obviously the planet. So the very, very important reaction. So the position of equilibrium is important in determining the most economical method for doing this, but you will see there needs to be a compromise with these types of reactions. So here's the reaction here, the Haber process. Very simple reaction. Nitrogen plus hydrogen will form ammonia, and the reaction going forward is exothermic, minus 92 kilojoules per mole. So pressure, let's look at the different kind of scenarios here. So pressure, high pressure will favour the forward reaction, which means you get a higher yield of ammonia, and that's good. Remember, that's what you want to produce. You want to produce ammonia. Equilibrium shifts to the side with the fewest number of gas moles. So there's 4 on the left and only 2 on the right. So if we increase the pressure, it will shift to the side with the fewest number of gas moles, and that's on the right. So that's good. So if we increase the pressure, then we get more of this product, and the reaction's faster too. So if we can produce this faster and produce more of it, that's a win-win situation. So that's favourable, increase in pressure. However, the difficulty is high pressure systems are expensive. You need vessels which can hold that kind of degree of high pressure. That costs a lot more. They can also be dangerous because you've got explosive risks as well. So a compromise has to be struck when we're looking at the Haber process. And so therefore we establish a pressure of 200 atmospheres for this reaction. Okay, so temperature then. So high temperatures will speed up the rate of reaction, as the molecules will obviously have a lot more energy. So you'll think, oh well, then we'll just increase the temperature then. So that's a good thing. However, high temperatures will reduce the yield of ammonia. It might speed up the reaction, but it won't give you any more ammonia. And the reason why is if we increase the temperature, the reaction's going to shift in the endothermic direction, which is backwards. And you're actually going to produce more nitrogen and hydrogen and not as much ammonia. So that's not really that good either. So again, we have to come to a compromise and say, well, actually, we try and pick a temperature that kind of favours a fast reaction, so a reasonable speed reaction, but we're getting a reasonable yield as well. And so the temperature here is 400 degrees Celsius, because obviously if the reaction's too cold and we're not heating it up enough, it's just going to be incredibly slow, and you might get a good yield of ammonia, but it'll take you months to produce it. That's just no good. So these are the compromise conditions that we have to use. So you can see why equilibrium is important, because obviously it does dictate how reactions proceed, and this obviously affects us in everyday life as well. Okay, so let's look at another reaction. This is the contact process. It sounds a bit boring, the contact process, but it's actually useful because it makes probably one of the biggest and most mass-produced chemicals in the world, which is sulfuric acid. And sulfuric acid you would have used in a lab, but it's used quite often in raw feedstocks as well to make other products. So the contact process is a really valuable process, and it's used to make, obviously, sulfuric acid. Here's the reaction here. So the contact process reaction is 2 lots of sulfur dioxide, that's SO2, plus oxygen will form 2 lots of SO3, which is sulfur trioxide. Now this reaction is an exothermic reaction, so enthalpy change is minus 197. And obviously to make sulfuric acid, what we do is we need to convert sulfur dioxide into sulfur trioxide first. You'll notice this isn't sulfuric acid, but it's the important part of that. So the pressure, let's apply the same principle as what we did with the Haber process. So high pressure will favour the forward reaction. Obviously this has got 3 gas moles on the left and only 2 here on the right. So if you increase the pressure, it will shift to the side with the fewest number of gas molecules, and that's SO3. So that's good. That's a good thing. So increase in pressure will give us more of this, which is what we need to produce sulfuric acid. And obviously the reaction's faster too if we increase the pressure. But just like with the Haber process, it's expensive and it can be dangerous as well. So in the manufacture of sulfuric acid, we use a catalyst. So we use V2O5 or vanadium, as the catalyst. And it's used to catalyze SO2 to SO3, which is this here. And then SO3 is then bubbled through water to make sulfuric acid. So we do use a catalyst to help this reaction, obviously here, which is important. But obviously the catalyst doesn't actually have any impact on the position of equilibrium. It just speeds it up, that's all. So a catalyst is used here. So you do need to know that. With regards to temperature, a high temperature will obviously speed up the rate of reaction. Obviously, the reaction is quicker. The molecules have a lot more kinetic energy, so they're moving around a lot more. But high temperatures will reduce the yield of sulfur trioxide because obviously if we increase the temperature, annoyingly the reaction is going to shift to reduce the temperature, which is to the left, and this is going to produce more sulfur dioxide and oxygen, which isn't what we want. So realistically we need to reduce the temperature to get a good yield, but if we reduce the temperature too much, it'll take ages to actually produce the product. So again, just like with the Haber process, a compromise is established to make sure that we produce a decent yield of SO3, but in a decent amount of time as well. Okay, so you just need to be aware of this and talk about the Haber process and the contact process for these reactions in relation to equilibria. Okay, so kind of moving on to the kind of last, I suppose the last section of this topic, and this is where we look at acid-base reactions, and I'm going to introduce you to two chaps who are Bronsted and Lowry, and this is where these were chemists, they were Danish and British chemists, and they collaborated to come up with a theory to explain how acids and bases work. Now, acid-base reactions are classic equilibria reactions, so this is why this bit's in here. But this is going to particularly talk about some particular reactions and what acid-base are. So Thomas Lowry is obviously the British scientist, British chemist, and Johannes Bronsted was the Danish chemistry, and these two worked together as a lot of scientists do, and they came up with a theory, and they literally thought, well, we're going to call this theory a Bronsted-Lowry theory, so they literally named it after themselves. You find a lot of scientists do. They like to kind of stick their names to it. And why not? It's a good achievement. So Bronsted-Lowry acids, they basically said that these acids are proton donors, so they give up protons. And so when we mix acids with water, hydrogen ions are released. That's basically what they're saying. So we take an acidic substance, dissolve it in water, obviously forms the acid, then H plus ions are released at this point. And these H plus ions don't exist on their own in water. They actually, in reality, form something called hydroxonium ions, also known as hydronium ions, which are actually H3O plus. That's officially what's in the water. And it's obviously these what makes it acidic. Just for speed, we're going to represent the acid as H+, but in reality, just be aware that actually what makes something acidic is H3O+, not just H+, okay? So, let's look at an equation here, and I'm going to use, just to kind of shorten it a little bit, I'm going to use HA, so Ha, very funny. HA is an acid, so H for the proton, A for acid, plus water, and that'll form H3O plus and A minus. So obviously that's the hydroxonium ion that makes things acidic. So Bronsted-Lowry bases are proton acceptors, so these will accept protons. So when we mix bases with water, they react with H plus ions to form hydroxide ions, and it's OH minus ions. Normally we use that to represent a base, so that's OH, obviously that's OH minus. So here's an example. So B for base, pretty straightforward. Reacting with water, and that'll form BH plus OH minus, and it's this bit that's the interesting ion here. So bases will have this OH minus, and acids will have this H3O plus or H plus for short. Okay, so let's have a look at some acid-base reactions here. Okay, so they can either be weak or they can be strong, and equilibrium plays quite a big role in this as well. So remember, when acids and bases react with water, they form a reversible reaction. So just to kind of bring these equations from the previous slide, acids, HA plus H2O forms H3O plus and A minus, and there's your base equation as well. So strong bases, so these dissociate or ionize, check that out for a word, almost completely, okay, and weak bases dissociate poorly. Okay, so let's have a look at some examples. So strong acids dissociate almost completely, weak acids dissociate poorly. So let's have a look at some weak acids first. So weak acids, so these are carboxylic acids, and you'll see a little bit of this later on in the organic chemistry section of year 1 if you haven't done it already. But things such as ethanoic acid and other carboxylic acids are classed as weak acids. So they normally have this equation, this type of reaction here. So they're in equilibrium. So you've got your carboxylic acid, and you obviously have your carboxylate ion and H+. So it's that bit which makes it acidic. So the backwards reaction is favoured, so you don't really get many H+ ions. So you get a lot of this, but not a lot of this when it's in water, when it's in solution. So because you don't have many of these, it's not really acidic. Strong acids, on the other hand, so these are things like what we call mineral acids. So HCl, sulfuric acid, nitric acid, these are your classic examples here. The forwards reaction is favoured quite strongly in these reactions, so you get a lot of H+ that's being produced. So equilibrium is pretty much wholly to the right. If anything, I mean, this really should just be an arrow pointing to the right. So these will dissociate freely, and you'll get loads of H+ ions and loads of Cl- ions. But it's this that makes something acidic. The more of these you've got, then obviously that makes it a stronger acid. Strong bases. So these are things like sodium hydroxide, potassium hydroxide. Again, the forward reaction is favoured strongly, so you get loads of OH- ions with strong bases. Your weak bases are things like ammonia. So ammonia doesn't actually have an OH within its molecule, so it actually needs to react with the water to create the OH- ion. But again, this reaction is heavily to the left. You don't have much of the OH- ion, and this is why molecules like ammonia are classed as weak bases, as opposed to sodium hydroxide and potassium hydroxide, which are a good bit stronger. Okay, so they're your strong bases, and obviously they're your strong acids there. Okay, so let's have a look at some conjugate pairs. Again, this is just really here for a little bit of information. You're going to need to know a lot more about this in year 2, so I wouldn't worry too much about this. It's just to kind of introduce it, I suppose. So any species that has gained a proton is a conjugate acid. So basically, an acid is obviously something that kind of gives up a proton, so the conjugate is going to be the one that that's gained it, and a species which has lost a proton is the conjugate base. So Bronsted-Lowry acids and bases react in this equilibrium here, and you can see it there. So there's your acid, there's your base. It forms BH plus and A minus, which you can see on there. So HA is the acid in the forward direction, because it donates a proton. So you can see it was HA, and the A is now on its own. So clearly that A has lost the H. So that's definitely the acid. And A minus is a base in the reverse direction, as you can see here, because it accepts the proton to form HA. So that's obviously the base in that point there. So we have what we call a conjugate pair. So them two are kind of linked. So the conjugate acid is HA, and the conjugate base in this case is A minus. So the HA, the A is giving up the proton, so that class is an acid, but going backwards, that has received the proton to form HA, so that's why it is a base. And obviously we have another conjugate conjugate pair with B and BH plus as well, and obviously the black arrows just show where these pairs are. So water reacts with acids as well to form H3O plus, which is your conjugate acid, and it reacts with the base to form your conjugate base as well. Okay, so let's have a look here. And so there you go. So you got your two different reactions there. So you got the base reacting with the water to form BH plus and OH minus, and that's what makes it basic. And then HA reacting with water as well will form H3O plus. Obviously that's what makes it acidic as well. So really this is just showing you the different kind of what it's just getting you to think about what an acid is and what a base is. Conjugate pairs really only comes into year 2 chemistry, but it just thought of introducing it here fits in quite nicely with what's been mentioned. It just reinforces what you need to be thinking about when you're thinking about a Bronsted-Lowry acid and a Bronsted-Lowry base. Okay. Right, so let's have a look at some acid-base reactions. Okay, so obviously when acids and bases react with each other, protons are exchanged. So this is, obviously that's what Bronsted-Lowry came up with. So let's have a look at this generic example of the acid, which is HA, and it donates a proton to the base B, and you've got positive and negative ions are obviously produced as a result. So remember, this reaction is in equilibrium. Okay, this is what the topic's all about, equilibria. So if we add more HA or B, then equilibrium will shift to the right to use it up. On the other hand, if we increase BH plus or A minus, then equilibrium will shift to the left because it will try and use it up. So remember, this is Lecitelia's principle, where he said if you try and impose a change on something, it will try and do the opposite. It will shift to try and counteract that change. So water actually behaves as a base when acid is added to it. So if you notice in this reaction, we've got the water molecule here, this one. It's accepted a proton to form the hydroxonium ion. So water here is a base. Now that's weird because you might think of water and think, well, it's neutral, isn't it? It's in the middle. But water will change how it behaves depending on what it's reacting with. Now, all you're looking for in these reactions is what has accepted the proton, and that must be a base. Anything which has donated the proton is an acid. So clearly water here is a base because it's accepted the proton to form H3O+. So that is a base, and that is an acid because that's given up the proton to form A-. So with strong acids, remember equilibrium lies well over to the right, if not basically you produce all of these, you produce 100% of these. Weak acids, it lies over to the left hand side here. You don't get much of these whatsoever, and that's why they're classed as weak acids. Okay, so acids react with bases to form salts, and they are pH neutral, as you probably be aware of anyway. So the H plus ions produced from acids, they react with OH minus ions produced from alkalis, and we make water, which is neutral. So therefore we can say the concentration of H plus is equal to the concentration of OH minus. So we can't have one without the other, so the concentrations are the same. So when we react an acid and a base together, the base, OH minus, comes from the base, H plus comes from the acid, and we produce water, which is the product there. So let's have a look at this reaction. We've got HCl, hydrochloric acid, reacting with lithium hydroxide, that's your base, and that forms lithium chloride and water. So there's your neutral product there. So salts are made from the metal from the base, okay, which is this bit here, or an ammonium ion, it depends on what's actually reacted, and the non-metal of the other than the hydrogen from the acid. So here you've got the non-metal from the acid other than hydrogen and the metal from the base, and this will form your salt. So this is your salt here, which is lithium chloride, and obviously water is produced as well. So let's have a look at another example. This is nitric acid reacting with potassium hydroxide, so that's KOH, and that'll form potassium nitrate and water. And let's do it again. There we are. So you've got the metal from the base and the non-metal bit from the acid, apart from hydrogen, so this is NO3, and that forms potassium nitrate. So when you're writing these equations out, it's really important that you are able to kind of identify which bits come from where and write the correct salt down when you write these reactions. Like I say, you've got to be a little bit careful with ammonia. Ammonia doesn't actually produce, as I mentioned before, it doesn't actually produce OH minus ions directly. So what it does is it reacts with the water first, it accepts a proton to produce ammonium ions, which is NH4 plus and OH minus ions. So you can see here, you've got NH3, which is ammonia, reacting with water, and that forms ammonium ion, and there's your hydroxide ions. So ammonia doesn't actually have OH minus ions already, it has to use the water to actually produce them in the first place. So ammonia, like I say, it reacts with acids to make ammonium salts, but you don't actually produce any water at all. So you can see here ammonia reacting with sulfuric acid, for example, that will just combine to form ammonium sulfate. So that's the only kind of exception here, and obviously that is a salt, but no water is produced at all. So just be aware of that type of reaction. That's obviously a weak base that we'd seen before. Okay, so just kind of looking in towards the kind of last part, I suppose, of this topic. this is where, and you probably will have done titrations, or you should have done anyway, so far. But obviously we can plot titration curves, so we can titrate acids and bases together, and we can basically monitor the pH level of the obviously mixed substance in the conical flask, underneath the burette. And we can do titrations with a combination of different strong acids and weak acids, and strong base and weak bases. So these graphs show the pH against volume of base added from a titration, and we're going to show different combinations of these acids and bases, as I said before. So you need to be aware of this. So you can see here, we've got a graph here just to kind of show you. So you've got pH, which is up along the side there, from 0 to 14, and we've got the volume of base added. So in the conical flask below, underneath the burette, we have acid in there. So it starts off quite acidic. Obviously the pH is quite low, isn't it? And it's a strong acid, so it's well down here, very low down at the bottom. Then when we start titrating or adding strong base, the pH gradually increases, okay, just gradually. And so you keep adding and keep adding and keep adding. And what we're doing, we've got a pH meter in there, and we're just measuring the pH at regular intervals. And then it shoots up, and then it goes obviously towards pH 14 because we've added a strong base. So it's a really pronounced curve that's produced, okay? And you're expected to be able to sketch these curves depending on what's being used. So if we look at a strong acid and a weak base, you can probably see the differences here. So we start off with a strong acid in the conical flask, because that's obviously a really low pH. But a weak base isn't obviously as powerful as a strong base, so the graph doesn't rise as high as 14. It'll probably go to about maybe it's pH 9 or 10 or somewhere around there. So we still get that kind of S-shaped curve, but it's not as tall as that. Now, if we look at weak acid, strong base, so we're starting with a weak acid in the conical flask, and you can see it obviously starts quite high up the kind of the graph here. So pH 5, somewhere around there, is a weak acid, and then we titrate that, add your strong base, and that shoots right up to pH 14. So you get that obviously S-shaped curve, just a little bit higher up. And the other one is weak acid, weak base, and to be honest, these are not great, to be honest, because you don't really get this defined end point here, which is this bit. So it starts off about pH 5 and ends about pH 7 or 8. So these are really difficult to judge where the end point is with these types of reactions. You can see that it's not really as defined as like that, where it's a little bit easier to judge. What you're expected to do is, if you're given information, you're expected to identify what's strong, what's weak, and from these graphs here. So just make sure you're aware of that. Okay, so we need to understand obviously certain features of a titration curve as well. So we're going to kind of just talk through these on here. So obviously we'll take a strong acid, strong base, because it's the one that's easiest to read. So we've got something which is the vertical bit called the equivalence point, or the end point. And if you've done titrations, you'll know that it's at the end point. You might get a colour change. If you've got an indicator in your conical flask, it might just suddenly change colour like that, and then you stop, don't you? And then you measure how much you've added in. So that bit is where you've got a sudden change in pH in this case here, okay? So it's at this point the acid has been neutralised fully by the base, and you get a sharp vertical rise, shows that rapid change in pH, because all of a sudden it's now quite basic. So it's at this point here, that's when you've got a fully neutralized substance. So the change in pH is smallest when you use a weak acid and a weak base, obviously, as you could see before. So it's not really that accurate. It's really difficult to find that endpoint. And clearly, if we start with the base first, then obviously the graph is just going to be the other way around. So if the base was in the conical flask and we're adding a strong acid, then it's going to go look something like that. But the principle is the same. There's no real difference there. Okay, so using titration curves and kind of looking at this, when you do these titrations, you generally, obviously we've used a pH probe to measure and monitor pH and plotted that on the graph. But in reality, if you're not interested in what the pH is, you just want to know where the end point is, we use an indicator. So you add an indicator into the conical flask, and when the indicator changes colour, you know to stop and take your measurement on your burette. So picking the right indicator is really important. Obviously, you've got to pick an indicator where the colour change happens at the end point in that vertical bit of the graph. So you've got to choose the correct one. And what you're looking for is an indicator that changes entirely within the vertical part of the titration curve for it to be effective at determining the end point. If it doesn't, you're going to have some problems, aren't you? So in this example, we've got to choose an indicator that changes colour between a pH range of 3 and 10. If it doesn't, if it changes colour any other time, it isn't going to work properly. So there's a variety of different indicators that can be used. However, two of the most common ones that you might have heard of are methyl orange and phenolphthalein. So they're your two indicators that you have. So let's have a look at the colour changes. So methyl orange has a colour change between 3 and 4.5. Okay, so that's the colour change. So you can see the colours there for methyl orange. And for phenolphthalein, the change is between 8.2 and 10, and that's when you've got your colour change there. So you can see methyl orange is red at low pH and yellow at high pH values, and it can be used for strong acid, strong base reactions, so that's fine. And it can even be used for strong acid, weak bases as well, because obviously that will change, that colour change will happen within that region. If we look at phenolphthalein, it's colourless at low pH and it's pink at high pH values. It's a lovely fuchsia pink. It literally is that colour. It's lovely. And it can be used for weak acid, strong base reactions. So obviously in this example, it's going to work quite well. For either one of these will work quite well because they both change within that zone. Obviously, your weak acid, weak base titrations that we've seen before, no indicator is really suitable for that. No indicator will change in such a narrow range that's required. So really, for them type reactions, you have to use a pH meter and try and judge when it goes to pH 7, which is your neutral position. So that's what you should use there. It's difficult to get indicators for that. Okay. And that's it. So that's the end of the equilibria topic. Quite a lot of information there, a lot of calculations. Go back, check your ICE tables, make sure you're able to work out what Kc is and Kp and partial pressures and mole fractions and things like that. Make sure you're able to be comfortable with that. The key thing with this is practice, practice, practice. Like I say, these slides are available from the test shop. Please go and have a look. You can purchase them. Really good value for money, good for your revision. Click on the link in the description box below and you'll be able to get a hold of them there. And please subscribe to the channel as well and show your support. I'll be massively grateful. All right, that's it. Bye-bye.